So till now we have learned some kind of classifications and regressions algorithms. So like KNN, naive Bayes, logistic regression. We have already learned these kind of classifications and regression algorithm. Linear regression, SVM. We have already learned these techniques. Okay, and if you remember KNN, this KNN is simple the instant based method. Instant based classifications method means for if we have a given in the query point, and from this query point we have we have find the k nearest point from this query point, and according to the majority board or something else we've decided what will be our output of this query point. So this KNN will be simple a instant based method. Now if you just remember naive Bayes, if you remember naive Bayes is simple a probabilistic method. According to just we are using some bias theorem and some conditional probability definitions, we are building the naive Bayes classifier. It is a probabilistic method. Okay. Now the logistic regressions, linear regressions, support vector machines, all these are based on geometrically. Means here we have defined some hyperplane to divide our class levels in our whole space. So this logistic linear actually they have some probabilistic interpretations also, but the main intuitions of these algorithms are from coming from geometrically. These algorithms are based on geometry. Okay, and here corresponding for age corresponding for the age algorithms, we draw a hyperplane. We draw a hyperplane for age. For also you will see the main advantage of the SVM is here we are considering the kernel tree, as well as for logarithmic regressions. For logistic regressions we also use the kernel tree, but the main specialty of SVM is for its time complexity. Its kernel tree is most famous. Kernel tree. Okay, these are till now we have seen, these are the some classifications as well as regressions algorithms. So the decision tree, now in this lecture, this is the first lecture of the in the series of decision tree. In this series of lecture we will learn decision tree. So decision tree is simple a conditional decision based algorithms. Means here we are using the if else conditions to find the class levels of a query point. Okay, so simple decision tree, in short I am using DT, is a nested if else based classifier. Okay, now let's discuss this thing first through an example. I think this will be better for us. Suppose let's take EDA example. Suppose let's take iris dataset example. So iris data, just searching on Google or Wikipedia iris data, then you can easily find there have set of 4 features. That is, iris is one kind of flowers. So in this flower the scientists collected this data set like that. They have 4 kind of features. The features vector xi is like that. They have four features, that is sepal length, petal length, sepal width, and petal width. Okay, they have these four features for each flower, and corresponding output will be these three classes. It will be setosa, virginica, that is, let's take, I'm not remember what is the flower name. See, actually iris is one kind of flower. There have three groups of flower for the iris, and they are classifying this group of flowers. They have the three groups of flower: the iris, setosa, virginica, some such kind of like that. If you just interest, just search it on Google, iris dataset, then you can easily find about these datasets. So there are these four kind of features: the sepal length, pedal length, sepal width, and pedal width. Okay, and corresponding the age features. Suppose let's take this is the features 1, this is the features 2, this is the features 3, this is the features 4, and corresponding age features, they are have the class level. Let's take the class level is 3 class level, A, B, C. 3 class level means there are three kind of flowers. Okay, A, B, C. According to this, we have decided which will be our flower, which will be our flower. So this is the simple data set of the iris data set, like look like that. Okay, so just if you just see this, if you just search it on Google, then you can easily find that there have some conditions. The conditions is what? Suppose our sepal length, suppose I am taking here, suppose simple, if this our sepal length, that is features 1, that is features 1, if this less than some value, suppose let's take this value is less than, suppose less than 5, then our class level will be, then our yi will be, suppose let's take A. Okay, this kind of conditions they are have. Just if you just see these data sets on Google or Wikipedia, I think it will be better if I show directly from the Google or Wikipedia. Okay, then I think it will be more visualizable how the things works. So this is the simple structure of the iris dataset. I'm taken I'm taken this picture from the Google image. Just you can search it on Google iris data, then you can find this data set easily. It is available, freely available on Google. Okay, this is the simple, thus sepal length, sepal width, petal width. This is the our features. Simple, this is our features vector. The feature 1, feature 2, feature 3, features 4. Okay, and simple, this is the output of the class level. Output, that is OII. There have three kinds of flower, that's like setosa flower, virginica flower, and this kind of three kind of flower. Suppose let's say A, B, C, like setosa, virginica, and I think one another. And they have some kind of data set. This is the look like data, iris data. Okay, and the thing is that they are, if you just analyze clearly, then if the petal length is less than is equals to 5, then we can conclude that our class level will be A. Suppose setosa means, suppose let's take setosa means equals to A, arsenica means, suppose let's is equals to B, and another one is equals to C. Okay, and suppose let's take, if you see the petal length, if our petal length is less than is equals to some number, it will be some less than some number. It will be, suppose let's say it will be less than x. If our petal length is less than x, then our class level yi will be suppose let's will be 1. This kind of data set. Now this thing is actually the iris data set. I think you have understand the thing, how the iris data sets look like. And so just I have taken this thing as an example to understand how this actually work. So simple, this is the simple and algorithm. This is the simple algorithm, how this class level is work. So actually here our data xi is in 4 vectors. 4 vectors means this kind of vectors. There are sepal lengths for some real number, Here have petal length, some real number it is, sepal width and petal width. These have some numbers. And corresponding to the corresponding edge data, we have checking conditions. We have apply here the if else conditions. If suppose if our petal length, suppose less than suppose x1, suppose less than x1, then our class level, let's our class level a. Else what? Else suppose else else if our suppose let's take our sepal length is than x2, then our class level will be b. Else our if our else otherwise our class level will be what? C. This is simple called the loop, if and loop, and this is the nested if and loop. So this is the if checking conditions, means you have first checking is and then else, and under these conditions this we also checking. This is called the nested if and loop. This is the simple model of the, this is the main central idea of the decision. This is the main central idea. This is the crack of the decision tree. This is the main central idea of the decision tree, and this thing is called the nested if else loop. This is called the nested if and loop, if else condition. Okay, so this is the simple programmatical view. This if nested if else conditions is programmatical view. If we just draw this same thing, just I am drawing this same thing in a tree, like tree, just if you remember when we are learning the KD tree in KNN chapter, so then you can see the how a binary classifier tree, binary BST, binary decision tree, and KD tree, how this which actually is drawing. The same things also work here. Suppose first what? First we are checking if PL means petal length is less than is equals to x1. So first I am checking here if our petal length is less than is equals to x1. This is the first checking conditions, and there have two conditions occur. If it is yes or maybe it is no. If yes, then what? Then our class level, we declare that our class level will be A. Then we will declare. Okay, if no, then again we are checking. If no, then what? Then our sepal length, then we have taken the sepal length is less than x2. If there have maybe two chances occur, is yes or no. If yes, then we declare that our yi is equals to b. If no, then we declare that our yi is equals to c. Okay, these are the simple tree structure of the nested if and loop. Okay, this is the programmatical view, this is the geometrical view. This is the simple geometrical view. Okay, and the tree, this concept, this thing is actually called a tree diagram. And in this tree, the first node is called the root node. This node is called the root node or any authors call vertex, no problem. And the end node is called the leaf node. This one is leaf node, this one is also a leaf node, this one is leaf node. Okay, and the under this node is called the internal node. This node is called the internal node. Okay, and every internal node and the root node, they are always for a tree, they have one root node, and they have maybe chance for many internal node. In a tree, for every internal node we have checking conditions. This is the decision condition, check the conditions here. Or another language it may be called condition node, conditional making node. and this is the T diagram. Okay, so what we will see here, we have seen there are kind of three kind of nodes here. We have seen actually here we have three kinds of nodes. First node is called the root node. Second kind of node is called the last, that is where actually our class levels occur. This node is root node. This is first, it is checking the conditions. This is the condition checker node. Here in a leaf node we got our class level, and in the internal node we also got here some checking conditions. We also got here some checking conditions in internal node as well. So the non-leaf node, simple, if we consider these two nodes, leaf node and internal node, this is mean the non-leaf node. This node is called the non-leaf node. In non-leaf node, in a decision tree we have checking conditions. We have checking the conditions here. Okay, this is the simple structure of the tree. So I think the pictorial view of these conditions is clear, all of you. Now let's go to the geometrical intuitions of this node. The geometrical intuitions of decision tree. Let's go there. The geometrical intuitions. Suppose here I am taking this example, same example I am taking here. So here I am taking the same example, that is, if first I am checking if fader length less than is equals to x1. First I am checking this condition, then corresponding we have two output, it will be yes or no. If it is yes, then we have made a decision that our output will be a. If it is no, then we have make another checking another conditions, that is sepal length is less than x2, and there may have two conditions, yes or no. If it is yes, then we have conclude that our yi will be b. If no, I am conclude that our yi will be c. Okay, this is the simple conditions that we have taken. Okay, now how we'll draw this thing in pictorial. Let's see. Already we have seen that when we have learned the binary search tree BST, then we have already see this thing. Just again revisit this concept. Suppose let's take this is our pedal length axis and this is our sepal length axis. Okay, and in pedal length axis, first we have checking the conditions. If PL, suppose let's take here is equals to x1 pedal length. If PL is less than is equals to x1, means here we have partition this action into. So if as less than is equals to x1 means which regions I am talking about? I am talking about these regions. I am talking about these regions, the whole regions. In the whole regions, our PL less than is equals to, in the whole regions, our PL is less than is equals to x1. In that whole region. In these whole regions, our yi is equals to what? A. In these whole regions, or yi is equals to a. Now these conditions. Now if it is no, if no means if our value is greater than is equals to x1, then what happen? Then we have taken that SL is less than is equals to x2. Suppose let's take x2 is here, SL x2 is here, x2 is here, means SL is equals to less than x2. Just I am neglect these regions. Already we have taken these regions. Now I am just neglect these regions. Now we have taken these conditions. Our SL is less than is equals to x2. means these regions. If xl is less than is equals to xt means what? These regions. I am talking about these regions now. Okay, these regions. If these regions is true, then I am taking the decisions that our OII will be B. Now I am taking the decisions that our OII here, our OII is equals to B. And if no, then our OII will be C. So just see this green color, green line here. These regions. In these regions, what happens? In these regions, our OII will be C. In this is the simple geometrical view. Suppose let's take this is our first plane. This plane is called, suppose let's take, I'm taking another. Suppose let's take this is our first plane, pi1 plane. Pi1 planes means which conditions? Pi1 plane responsible? This plane. And second plane is what? This plane. Pi2 plane, this plane. Pi2 plane. This is what? For what conditions? This condition. This is this one. Pi2 plane. And the main thing is that our every plane, just if you see the first pi2 plane is parallel, axis parallel to PL. Our pi2 plane is parallel to PL axis, and our pi1 plane is parallel to SL axis. So simple, all our hyperplanes, all our hyperplanes are axis parallel. Okay, are axis parallel in this distance t. And the decisions is what? And the decisions are simple, our hyperplane. And the hyperplanes are the simple making the decision. The hyperplanes are making the decisions here. So in this decision tree, what we have learned? In the decisions we have see that it is the simple constructions of the nested decision tree, simple, built through the nested if else loop in programmatical. Just if you see this thing in programmatical point of view, it is the simple nothing, it is the simple a nested if else loop. It is simple a nested if and loop, a nested if else loop, and in programmatical point of view. And it is a set of axis parallel pies, that is simple, the set of axis parallel pies that will divided our whole regions into small regions. Okay, in geometrical point of view is simple, in geometrical point of view it is set of axis parallel hyperplanes. In geometric view, this is the simple central idea. This is the simple central idea of the decision tree. Nothing else. Okay, I think this lecture is clear. Okay, through these examples.